So we've been learning shortcuts for finding the derivative of functions, and all of the functions that we have looked at so far were explicit functions where y is dependent on x or y equals x. And so we haven't really talked about functions that are implicit or where it might take more than one normal function to define. So we'll look at some examples in a minute. But if I were to take the derivative of multiple variables in the same problem, then I've got to be able to distinguish among them. And so to do that, we're going to create kind of little tags that go along with each one depending upon which one I'm taking the derivative of. So far, we've always taken the derivative of x. So whenever I took the derivative, it was the derivative with respect to x. So the derivative of x was just 1. When I take the derivative of y with respect to x, then I get 1, but it's a dy dx. And that's why whenever we have a function like y equals x and we take the derivative, we can say dy dx equals 1. Because the derivative of y is 1, derivative of y with respect to x, equal to 1, which is the derivative of x. So every time we've done that, we only had to deal with y, and so we called it y prime or f prime or dy dx. But if I have a lot of different variables, then I need to determine each of them with a tag. And so the same is going to be true for all of these. The derivative of v would be 1, but if I'm taking it with respect to x, it's a dv dx, or 1 dt dx. And so that's the way this is going to work. Now in this next one, if I were choosing to take the derivative with respect to y for all of these letters, then this would just be 1. The rest of them would require the tag. So this would be a 1 dx dy. This one would be a 1 dv dy. And this one would be dt dy. If I'm taking the derivative with respect to v, this would be 1. And these would all have a tag. 1 dx dv. 1 dy dv. 1 dt dv. So the point here is that we can take the derivative of all of these letters, but if we're taking it with respect to x, or sometimes with respect to time, which would be t, then we have to give each of the letters that is not the same as the one we're differentiating a tag. So in our next example here, we're taking the derivative with respect to x, so the x's are just going to be normal. This would just be a 2x. But this one would be a 2y, but with the tag dy dx. This one 2v dv dx. This one 2t dt dx. So you can fill out the rest of these charts and then I'll check back with you. I'm going to fill them all in real quick and then you can check and make sure you have them all correct. Okay, so I'm going to leave these here for just a minute so you can double check your work as well. But all of the y's are going to have a dy with the lower portion being whatever you're taking the derivative with respect to. So dy dx, dy dt, the same with each of these. And here's your second chart. Same idea. So here it was t. We weren't ever taking the derivative with respect to t, so all of these had a different tag, dx, dy, and dv. All right, so let me just go back one more time. I think I kind of skipped through it because it was kind of an assumption, but I do want to point out that whenever I said these are just normal, like the x is normal because we're taking the derivative with respect to x, it is because this would be 1 dx dx. Well, a dx dx is just 1, so it's not necessary. So that's why each of these, this one would be a dy dy, just 1, so not needed. So they all really have a tag, it's just that some of them the tag is just 1. Alright, so examples of implicit functions and explicit functions. Explicit functions are the ones we're used to looking at, where you can solve for y easily. An implicit function would be something that looks like this, where even if I tried to solve for y, it would be very difficult to do it with just a single function. It might take more than one function to give that same equation, or it might be almost impossible to separate that function out. So what we're going to be doing here is taking the derivative with some functions with respect to x. We're going to differentiate with respect to x. And so in this one, which is an explicit function, when I take the derivative with respect to x, the y would be 1 dy dx. And over here, I would just get 4x with a dx dx, which means that I don't really have to have a tag. So this is where the dy dx that we just talked about, that's the same as y prime. That's where it comes from. Now over here we have an implicit problem. So this would be 2y dy dx equals 2 dx dx. Now in each of those, I still want to get dy dx by itself because dy dx is my derivative. And so in this one, to do that, I would need to divide both sides by 2y, move it over to the other side. So I would get dy dx equals, the 2's divide out, and I get 1 over y. So we are always going to solve for dy dx, or in this case, it's a dy dx. We're going to solve for that derivative. So these are the steps that we're going to go through when we're solving implicit differentiation problems. We're going to differentiate both sides of the equation. If there happens to be something more than one term with a dy dx, we're going to collect all of the dy dx's on one side. And then once we've done that, we'll factor out the dy dx, and then we'll be able to solve. So let's go ahead and take a look at one. We're going to have the derivative of x squared just be 2x. And then here, we're going to have a product rule. So we have minus the first times the derivative of the second. The derivative of y is a dy dx. Plus the second, y times the derivative of x, which is just 1, plus 2y dy dx equals 0. Don't forget to take the derivative of the 7 as well. So I'm going to distribute here. We have 2x minus x dy dx minus y plus 2y dy dx equals 0. So we have two terms that have dy dx. We're going to keep those over on this same side. And we're going to move the other two terms, the 2x and the minus y, to the other side. So we're going to have y minus 2x. So now we're down to the step where we're going to factor out the dy dx. So I have not equals. When I factor out the dy dx, I have negative x plus 2y equals y minus 2x. And so I'm going to solve for this dy dx by dividing by negative x plus 2y. So dy dx equals y minus 2x over negative x plus 2y. All right. So example 4. we're starting off with a product rule. We have first times the derivative of y, which is the dy dx, plus the second, which is the y, times the derivative of x squared, which is 2x, plus, and then we take the derivative of 2y cubed, so we get 6y squared with the dy dx, equals derivative of 3x is 3, plus 2, and then a tag of dy dx. So all of the dy dx's move to one side. I'm going to keep those over here on my left hand side. So I'm going to move this one over here with them. And then I have the 3 still on the other side, and I'm also going to move this term, the plus, which would become minus 2xy. Now I factor out the dy dx, and I have left x squared plus 6y squared minus 2. And then we divide x squared plus 6y squared minus 2. So dy dx equals 3 minus 2xy over x squared plus 6y minus 2. Oh, sorry if you can see me. There we go. Give you a chance to catch up on that one. Alright, so our next example has some trig in it, but still doing the same thing. So here we're going to have a chain rule. The derivative of the outside, we have cosine, inside stays the same, times the derivative of the inside. So the derivative of x squared would be 2x, plus the derivative of y is dy dx, equals, and then on the right hand side we've got a product. Now if you wanted to, you could distribute and then take the derivative, but I'm going to go ahead and use the product rule. So we have the first times the derivative of the second, which is just 3, plus the second, 3x plus 1, times the derivative of the first, 2y dy dx. All right. So over here on this left-hand side, remember this is a single term, so we do need to distribute that into our binomial here. So we're going to have 2x cosine of x squared plus y plus cosine of x squared plus y dy dx equals all of this other stuff. So we have 3y squared, and again over here we have a binomial and a monomial, so we want to distribute. So we have, let's see, 6xy dy dx plus 2y dy dx. All right, so our dy dx terms, we've got one here, we've got one here, we've got one here. So I'm going to again move those to the left. So cosine of x squared plus y dy dx minus 6xy dy dx minus 2y dy dx equals, and then we have the 3y squared that stays over here, minus our first term, 2x cosine of x squared plus y. All of our terms on the left, we're going to factor out the dy dx. So we have cosine of x squared plus y minus 6xy minus 2y equals 3y squared minus 2x cosine x squared plus y. And we're going to divide by all of these terms. Cosine x squared plus y minus 6xy minus 2y. So all of those are gone, and I have my answer. Dy dx equals this term, or this rational equation here. We've got 3y squared minus 2x cosine of x squared plus y over cosine of x squared plus y minus 6xy minus 2y.